This video is to introduce you to the symmetric group Sn. Sn is equal to the set of all mappings mapping a set A to itself, where sigma is a one-to-one. In other words, Sn is a set of one-to-one functions from a set A to itself, and the set A is equal to the set containing 1, 2, 3, up to, and including the positive integer n. So in other words, let's look at one example in S3. We're going to map the set 1, 2, 3, and we're going to map it to itself. So here's A, and here's A, and here's an example of a permutation. Might map 1 to 2, map 2 to 3, and 3 to 1. That's an example of a one-to-one mapping. The red lines represent the elements of Sn, not the numbers in A, but the mappings. So Sn we're going to show is a group under function composition. And by the way, let's take that red mapping there, and let me show you a way that we often write this. Sigma was the name of the map, and I write 1, 2, 3 up here, and then I write the image of 1 underneath it. So 1 went to 2, 2 was mapped to 3, and 3 was mapped to 1. So this mapping here, this is a way to write that. The purpose of actually this video and video 9 is to get you able to comfortably work within the group, to calculate in the group, and to understand some of its subgroups. It's a very important group. One of its subgroups is extremely important in group theory. So we'll spend the time necessary to get comfortable in Sn. And by the way, the video after this, video 9, is I made for 19 students that I had at Buffalo State College in, I think it was 2013 or 2013, and almost 12,000 people students from around the world have looked at that video. So it's not easy to get familiar with this group, and I think that the videos will do a good job helping you. Well, first let's prove that Sn is a group. Remember, the elements of Sn are the mappings. So the operation will be function composition. We know that function composition is associative. We know that the identity mapping would be the map from A to A that sends each element to itself. So really all we have to do is show that if sigma and phi are in Sn, that so is sigma phi. We have to show that it is a binary, function composition is a binary operation. And remember, that just really means showing closure. Sigma phi in Sn, we need to show that sigma phi is in Sn. The membership rule for Sn is that whatever is in there is a one-to-one mapping from A to A. So that's what we're going to prove. So in red you see the proof tip that I've written before. To show two functions are one-to-one, or to show a function is one-to-one, we assume that f of A equals f of B and show that in that case A must be B. So we proceed that way now. We have let sigma and phi be two elements of Sn. So they are each one-to-one mappings. So let's write that down. Sigma maps A to A, and phi maps A to A, where A is this set here, and they are both one-to-one. Sigma and phi are one-to-one. So we suppose now that sigma of phi of A is equal to sigma of phi of B. Remember, sigma phi means sigma circle phi. Oh, well, sigma is one-to-one. So that implies that phi of A is equal to phi of B. And now phi is 1 to 1, and this implies then that A is equal to B. So if sigma phi of A is equal to sigma phi of B, we know that A is equal to B. So we can conclude that sigma phi, or you can think of it as sigma circle phi, phi is 1 to 1. To define sigma inverse for a given sigma, we have to remember that these one-to-one functions from A to itself, let's say sigma mapping A to A, is not only one-to-one, but it is also onto, because it's mapping A to itself. So we can define sigma inverse as follows. Let sigma inverse of A be equal to B, where sigma of B is A. We know B exists because this sigma is 1 to 1 and onto. So this gives us our inverse, and you can quickly see that sigma inverse sigma is the same thing as sigma sigma inverse, which is the identity map. This group is called the symmetric group on n letters and is denoted by Sn. We need to get down the notation to use for these permutations. This will be the standard notation, and then we're going to switch to something much better. But we can indicate a mapping, an element of Sn, by simply writing one of these square bracket matricey type notation here. And we're using n equals 3. So we write the elements of A on the top, 1, 2, 3, and then right under them we write their image under sigma. So for example, row 0 here, that's our identity. I named it something else when I wrote this. Row 0 maps each element to itself. Look at mu 3, maps 1 to 2, 2 to 1, and 3 to 3. In other words, you could think of that as being 1, 2, 3, write 1, 2, 3 here, and then the mapping would be 1 to 2, this is mu 3, 1 to 2, 2 to 1, and 3 is, we say, fixed. It maps to itself. That would be mu 3. We have six of them. That shouldn't be too surprising because we see that you have 1 has 3 choices to map to, and then once 1 is mapped to something, there are 2 choices for 2, and then only 1 choice for the third. And so 3 factorial is the number of elements in S3. So now we're going to compute using row 1 and mu 3. I want to compute the mapping row 1 mu 3. Excuse me, row 1 mu 3. In other words, row 1 of mu 3. And to do that, we have to see what it does to 1, where it maps to, and where it maps 3. So let's do row 1 mu 3 of 1. That is row 1 of mu 3 of 1. So we look up here at mu 3, and we see that mu 3 of 1 is 2. So this is row 1 of 2. We go up to row 1, and we see that row 1 maps 2 to 3. So this is 3. And if we're making let's draw it right up here. 1, 2, 3. We just found out that row 1 mu 3 of 1 is equal to 3, so it sends 1 to 3. Now let's do row 1 mu 3 of 2. That is row 1 of mu 3 of 2, and mu 3 of 2, you see, sends 2 to 1. So it is row 1 of 1. Row 1 of 1 is 2. So we know that this row 1 mu3 mapping sends 2 to 2. So it fixes 2. And we know now that 3 will be mapped to 1. But let's verify it. Row 1 mu3 of 3 will be row 1 of mu3 of 3. And mu3 of 3 is 3. So this is row 1 of 3. And row 1 of 3 is equal to 1. And that's just what we needed. We knew that 3 had to be mapped to 1. So this is the mapping, row 1 mu3. So what we have found here is that row 1 mu3 equals mu2. So here is row 1 mu3, and this entry will be mu2. I think that you should try to fill them in on your own and check yourself. You get one mapping in each box. I computed one more for you here. You can put it on pause and make sure you could do this. I calculated mu1, row 1, and I just calculated what it did to 1, 2, and 3, and then I put it in this notation, and I looked back and I saw that that is mu2. So mu1, row 1, is mu2. The way that we will use notation for these mappings is not this. It's much easier. We use cycle notation, but it takes some practice. Notice that this is just a cycle. It takes 1 and it sends it to 3. And then it picks up 3, 1 to 3. Then it sends 3 to 2, and 2 back to 1. So we call this a 3 cycle. And instead of using this notation, we just use this. Row 2 is equal to the cycle that sends 1 to 3, and 3 to 2, and 2 back to the starting point 1. This parenthesis here, the right parenthesis, just indicates that 2 goes back to the beginning. So this is the cycle notation for that permutation. Now here I give you a sigma, a mapping given cycle notation, and let's see if we can translate it into the notation that was first described. If you look at this cycle, this is a product of a 3 cycle and a 2 cycle. Sigma is. And notice that they don't overlap. This is one permutation. It sends 2 to 4. All right, well, let's just write a 4 under the 2. It sends 2 to 4, and 4 back to 2 because the parentheses are closed. So 4 goes to 2. This permutation sends 1 to 3, 1 to 3, and 3 on to 6, so 3 goes to 6, and 6, because the parentheses are closed, goes back to 1. Now notice that 5 was not written in this permutation. That just means that 5 is fixed. 5 goes to 5. You could have written this permutation as 1, 3, 6, 2, 4, and then just the 5 could be by itself, but we usually don't put it in. Now below, let's draw the cycles of this permutation. Here's, let's see, 2 goes to 4. Okay, so I would just, that's a 2 cycle, 2, 4. 2 goes to 4, 4 back to 2. That's the 2 cycle, 2, 4. And this cycle, I could have put them in either. I could have put the 3 cycle on the left, it doesn't matter. 1, 3, 6. And that cycle represents the 1, 3, 6. when cycles are disjoint like this, they don't share any elements of A in them. You don't see an element of A twice. That means it doesn't matter if you put this on the left or this on the right, or this could be on the left or right. In other words, it's a little early to tell you this, but disjoint cycles commute. And this, in fact, is one of the elements of the group. Now I'll show you how to calculate. We just looked at sigma, the 3 cycle and the 2 cycle, and here's a delta given to us in the bracket notation and also the cycle notation. Make sure that you can go from one to the other. But it sends 1 to 2, 2 to 5, 5 to 6, 6 to 3, and 3 goes back to 1. So it is a 5 cycle. Calculate sigma delta. Okay, well, we just write it out in order now. It's very important. The 1, 3, 6 and the 2, 4, you could switch. They commute together, but you've got to write 1, 3, 6, 2, 4 to the left of 1, 2, 5, 6, 3. And now, as we go calculate this cycle, we move to the left because this is function composition. And we need to see what does this cycle do to 1, 2, 3, 4, 5, 6. Once we find out that, we will be able to find out which of the 6 permutations sigma delta is. Here's how you do it. I always write 1 first. And then I'm going to go back up here and see what sigma of delta of 1 is. Okay, well, I don't have to be thinking which one sigma and delta because I wrote them in the correct order. So I just move to the left and I find 1. And 1 is sent to 2 by that cycle. So now I look for 2. 2 is sent to 4, and I don't see 4 again as I move to the left. So the product of these 2 cycles sent 1 to 4. Now I have to see what does this product of 2 cycles do to 4. What is sigma of delta of 4? So I go back to the right-hand end and move to the left until I see 4. I don't see 4, I don't see 4. Here it is. 4 in this cycle is sent to 2, back to the beginning of its cycle. I keep going to the left looking for a 2, and I don't see one. So 4 was simply sent to 2. Now we see what happens to 2. So I have 2 in my head, I go back to the right and move left again. And I'm hunting for a 2. Oh, here's one. 2 is sent to 5 by that cycle. Now I'm continuing and looking for a 5, moving to the left, no 5. So this product just sent 2 to 5. I write down my 5. I go back now and start looking for 5. Well, I see 5 here. 5 is sent to 6. Now looking for 6. Here I find it, and 6 is sent back to the beginning of its cycle because the right parenthesis is there. So 5 was sent to 6, and in turn 6 was sent to 1. So the product sends 5 to 1. 1 is at the beginning of the cycle, so I just close it. So we have a 4 cycle. Now I have to see what happened to 3 or 6, so I'll just write 3 here. I usually just write the next biggest number that's not already in the product. Okay, so we go back and see what happens to 3. So I find 3 right here, and I see that 3 is sent to 1. Now I'm searching for a 1, and I see that 1 is sent to 3. So this product fixes 3. So for now, I'll just close the parentheses. We could erase that later, or just omit it. And let's see, we better check 6. We haven't checked that yet. 6 is sent to 3, and 3 is sent to 6. So yes, 6 is fixed, and I would write this product as just the 4 cycle, 1, 4, 2, 5. You don't need to include those in the notation. You just assume 3 and 6 are fixed. So that is sigma delta. And that's how you calculate using these cycles. We'll do more examples, and in the next video there's lots more. This is just a reminder. Remember that the permutation, for example, 1, 3, 4, a 3 cycle, sends 1 to 3, 3 to 4. That is not, you have to be conscious of what A is. In other words, which group are you in? 1, 3, 4 is a different mapping in S4 than it is in S6. In S4 it fixes 2. In S6 it maps 2 to 2, 5 to 5, and 6 to 6. So for two functions to be the same, they have to have exactly the same domain, and they have to send each element in that domain to exactly the same element. The reason this group is an important group to study in a beginning abstract algebra course is because it is a great example of a finite non-abelian group with some very important subgroups. So let's practice these problems and then we're done. Here are 3 permutations in S6. In other words, they are all mapping. For example, sigma is mapping A to a one-to-one function, and A is the set containing 1, 2, 3, 4, 5, and 6. So we have 6 factorial mappings in there, and these are 3 of them. So first of all, write them in cycle notation. Okay, sigma equals, I write 1 down first. Now I go up here and I see sigma of 1 is 3. Right here. Sigma of 1 is 3, so I write 3. Now I want to know what happens to 3. So I go here and I see that 3 is sent to 4. And now I check 4. 4 is sent to 5. I check 5. 5 is sent to 6. 6 is sent to 2. And 2 back to 1. So sigma is a 6 cycle. Now let's do row. Row, I put my 1 in first, and I see that row sends 1 to 2. And 2 then goes on to 4. 4 is sent to 3. 3 is sent to 1. Well, 1 is back at the beginning, so I close. Now I have 1, 2, 3, 4. I need to see what happens to 5, so I stick it in. 5 goes to 6, and 6 back to 5. So we have a 2 cycle. So rho is a product of a 4 cycle and a 2 cycle, and mu is, I put my 1 down, 1 goes to 5, 5 goes to 1. I have a 2 cycle. Now I'll put in 2. I just put in the next number that I haven't listed yet in there. Put in. So 2 goes to 2, so I'll just close it. Now 3. 3, mu sends 3 to 4, and then it sends 4 to 3. So I close it. It's a 2 cycle. And we have 1, 2, 3, 4, 5. And I look up here and I see, 6 is sent to 6. Well, you could put it in, but you don't need to. Mu is, in simplified notation, would be the product of 2 cycles. 1, 5, 3, 4. Okay, so now this question asks us to compute row sigma. So write them down. Don't do them written up here. Write row sigma, the cycles. Now we compute. All right, I write down my 1. I go back to the right-hand end and I track what happens to 1. First of all, 1 is sent to 3. I look for a 3, and 3 is sent to, 3 is sent back to 1. So 1 is fixed. Okay, so I'll write down 2. Let's see, I start back at the right. I see that 2 is sent to 1, and 1 is sent to 2. So 2 is fixed. So now we try 3, put in 3, and I see that I start at the right, I go until I see 3, 3 is sent to 4, now I trace 4, and 4 is sent to 3. So 3 is fixed. Maybe this is the identity that we're going to get. Now we have to check 4. Put in 4, go back to the right, I see that 4 is sent to 5. I go down and find 5. 5 is sent to 6. No more 6s, so 4 is sent to 6. Now what happens to 6? Well, I go back. I see that 6 is sent to 2 by the first cycle. So I'm looking for 2, looking for 2. 2 is sent to 4, and that's good. We close it, and we see that 1, 2, and 3 are fixed. 4 goes to 6. Well, we do need to check 5. I mean, if it's not fixed, I've made a mistake, because it's the only one we have left. But let's check. 5 goes to 6 here, and going back down to the left, 6 goes to 5, no more 5s, and so yes, 5 is fixed. So our answer here would just be the 2 cycle 4, 6. And by the way, I haven't mentioned it, but little iota, if we want to call it little iota, the identity or row knot, as I did in this video, the way that it fixes everybody, so you can't just leave it blank. You usually put in just this, 1, in cycle notation. Okay, so sigma inverse. Well, here's sigma here. And sigma inverse, if sigma sends 1 to 3, sigma inverse has to send 3 to 1. It has to reverse exactly what sigma does. So the easiest way to write it is just to write the opposite. Just reverse your numbers. So here's where I will not put 1 first. I'll put 2, 6, 5, 4, 3, 1. Notice that sigma of sigma inverse will give you the identity. You just reverse the order. And so, for example, sigma sends 4 to 5, sigma inverse sends 5 to 4. Or you could say sigma inverse sends 2 to 6, and sigma sends 6 to 2. They reverse each other, they undo each other. So that sigma inverse is equal to little iota. Okay, m squared row. I put 1 down first. And then I go back and I see what happens to 1. So I start at the right. I see that 1 is sent to 2. And now 2, I keep going to the left. Nothing ever happens to 2 again. So the product sends 1 to 2. Now I go back to the right, and I want to know what happens to 2. So I go until I find it. 2 goes to 4. Now I'm searching for 4. 4 goes back to 3. And now I look for 3. 3 goes to 4. So 2 is sent to 4 by that product. Now we start on the right again. What happens to 4? Well, 4 is sent to 3 here, looking for 3. 3 is sent to 4 there, and 4 is sent to 3. So the product sends 4 to 3. Now I go back and I want to know what happens to 3. So I see that 3 is sent to 1, back to the beginning of its cycle. 3 is sent to 1, and then I find 1 is sent to 5, and then I go down here and find that 5 is sent to 1. So 3 is sent to 1 by this product, and I close the cycle. Now we need to know 1, 2, 3, 4, so we need to know what happens to 5. Going back to the right, I see 5 is sent to 6 here. Now looking for 6, I never see it again, so 5 is simply sent to 6. 6 is sent to 5, now looking for a 5. 5 is sent to 1, 1 is sent to 5. So 6 is sent to 5, and I close. So that is mu squared rho, written in a product of disjoint cycles. That's what you're trying to do. So now let's find row sigma inverse. So I write down row 1, 2, 4, 3, 5, 6, 4 cycle times a 2 cycle, and now sigma inverse, I just write it and reverse the numbers. So I reverse the direction of the cycle. So I write 2, 6, 5, 4, 3, 1. And now I will do as before. How many permutations are there in S6? Well, there's 6 factorial. For the same reasoning, there were 3 factorial in S3. And the last question is, oh, excuse me, I don't know if you saw me write that. How many permutations? 6. So you see that these two are not the same, and that is sufficient to prove that Sn is not an abelian group. Prove that S6 is not an abelian group. Well, let's just take 2 permutations, like I'll take 1, 2, 4 times the permutation 1, 3, 1, 3, 5. Those are 2 different elements of S6. They're 2 3 cycles, and notice they both have a 1 in them. So those are 2 separate elements of the group. And 1, 3, 5 times 1, 2, 4 won't be the same. To define sigma inverse for a given sigma, we have to remember that these one-to-one functions from A to itself, let's say sigma mapping A to A, is not only one-to-one, but it is also onto, because it's mapping A to itself. So we can define sigma inverse as follows. Let sigma inverse of A be equal to B, where sigma of B is A. We know B exists because the sigma is one-to-one and onto. So this gives us our inverse, and you can quickly see that sigma inverse sigma is the same thing as sigma sigma inverse, which is the identity map. This group is called the symmetric group on n letters and is denoted by Sn.